So why is that relevant to consolidation? Why is the UE relevant for consolidation? Well, let's understand the concepts. Let's begin to look at the fabric of a soil. So let's say, and how it acts under load, etc., right? So let's say that we have an assembly of grains, okay? So this is just 6 grains out of millions that compose a soil mass, okay? And let's say that they are rounded so that we can simplify the visualization, okay? Now, what happens? Let's say that a load is placed somewhere on top. So this group of grains correspond to a point that is located there, okay? There's many grains at this point, many more than 6, but let's say the 6 of them are in there somewhere, right? And a load is imposed. That load is a proposed field, okay? Let's say it's not proposed, it's a constructed field. So another layer is added to this site. Well, there will be a delta sigma z imposed at this point, right? So the particles are going to suffer additional forces between them, okay? Now, if the fabric of the grains is not perfectly organized as it is here, if there's some little defect, maybe these particles are a little bit bigger, etc., then locally the particles at the point will undergo or suffer some shear action, okay? So the particles are going to essentially move relative to each other and the soil will deform, okay? So a system like this will eventually end up like that, okay? And the way to, sometimes it's very interesting and very insightful to think of this, particularly when we talk about strength later on. If you go like this with your knuckles, sorry, I'm trying to focus here with the computer. Okay, so first, imagine the knuckles are the particles, right? They're like this, and if you impose a force on your arms, you're gonna end up like that, okay? Sorry for the wobbliness there, but that's basically the point. The particles will rearrange upon loading so that the system is denser, the soil becomes denser, okay? So what happens in terms of phase relationships? Well, the fabric or structure, okay, those two words are interchangeable, fabric or structure, is going to be altered during the densification process. What phase relationship will be altered mostly? The void ratio, because the volume of voids, that volume, essentially drops for the system to become dense, okay? The reduction in void volume is accompanied by the densification, or vice versa. You can say densification is accompanied by the reduction in void volume. Now, for the case of consolidation, we can think of this soil, for example. At this point, all of this mass of soil is saturated. So in here, that's where the water is. The water is filling all these voids. So if the soil densifies because of loading, then the water, some of it, not all of it, must squeeze out. Okay? Must squeeze out of the voids. And again, this is similar to taking a sponge with your hand, dipping it in a bucket of water, and then squeezing the sponge underwater. Okay? If you squeeze the sponge underwater, you basically densify it, but it's not desaturated. It's still saturated, just that some of the water inside the sponge escapes the sponge into the bulk fluid in the bucket when you squeeze the sponge. This is the same thing as consolidation. Okay? So this is basically consolidation from the perspective of just a couple of grains. Now, what about the UE? Where does the UE come in here? Well, you'll see that in the next slide, but let's talk about it just briefly here before we introduce that slide. What happens if the water has a hard time squeezing out when load is imposed? Well, the water will be pressurized by the action of the grains falling in the voids, let's say. Falling, it's not really falling, but they're moving towards the process of reducing the size, right? So if you take a syringe, for example, and fill it with water, and then place the piston of the syringe. If you go like this, the syringe is like that, right? So if you squeeze the piston of the syringe slowly, the water will come out of the needle and it will be fine, right? But what happens if you try to squeeze it very fast? Well, what happens is the water squeezes out very fast out of the needle, but if you do it very, very fast, the water it's not able to squeeze out as fast as you want to squeeze it. And in that case, the water inside the syringe will be pressurized, okay? And that pressure is a pressure that you impose by the force of your finger if you do it very fast, right? And so that pressure is the excess pore pressure for that system of the syringe. Okay, now, for soil, we have this particular slide that uses same type of approach with the particles, right? 6 particles, to explain that concept of pore pressure generation, excess pore pressure generation in soil. So again, we have our point. Water table, let's say, is at the ground surface, and then we place, as engineers, we construct another layer on top of that ground surface. By doing that, we load the soil at this point and every other point in here with an additional effective stress. The point suffers an additional effective stress. Okay. Now, here is the system of particles, of let's say 6 particles that are somewhere in this point. Okay? Now, let's say that we construct this fill very slowly. So we add a little bit, compact, add a little bit, compact, add a little bit, compact. And we take a long time to do this. Okay? Well, in that case, what we have is a loading rate. Remember, the rate is like saying speed, right? We have a loading rate that is very slow or low, right? We're constructing slowly. Now, as we are constructing, then particles are responding by being loaded, right? So the particles tend to want to do this. From this system, they want to attain this system, okay? Now, as the particles move relative to each other, right? They compress the fluid, and then the fluid has to escape the void, some of it, right? Consolidation. Now, how fast or how easy it is for the fluid to flow through the pores depends on the hydraulic conductivity of the soil. Okay? If the hydraulic conductivity is low, then it is very hard or difficult for the water to flow through the soil. That's why it flows slowly, right? If the hydraulic conductivity is high, then it's very easy for the water to flow through the pores because the pores are big, right? Generally, that's the case. So, the hydraulic conductivity dictates what's called the drainage rate, which is how easy or how fast the water will be able to escape the voids. Some of the water will be able to escape the voids so that the particles can achieve a dense configuration. Okay? So, what happens if we load very slowly, like we had said before? Okay? And let's say that on top of the fact that we load slowly, the soil is, let's say, is gravel. Okay, so it's a very high hydraulic conductivity. So we are loading slowly, and the hydraulic conductivity is high, so that the water can easily escape through the voids. Okay, in that case, we have what is called a drain condition, because the ratio of the loading rate, which is low in our case, the case of our example, the ratio of the loading rate versus the drainage rate is very high in our example because the hydraulic conductivity is high. That ratio is very low. So what this means is that we have a drain condition where the water drains out very easily, okay, and the void ratio goes down as the particles achieve this configuration. Okay. In this case, we can assume that UE is basically 0. Okay, so it's the syringe being squeezed slowly case. If you squeeze the syringe very slowly, the water is going to come out, will come out slowly, but the pressure inside the valve of the syringe is going to be hydrostatic. There's no added pressure due to your finger moving the piston. Okay? Now, on the other hand, what happens if we have the opposite effect, or the opposite situation, or condition? Okay? We have a fast loading rate, so we construct fast, let's say, this field, and on top of that we have a soil that has a very low hydraulic conductivity, like clay. Okay? In that case, the ratio is high. So what's going to happen? It's like pressing the syringe very, very fast. In that case, you are loading fast, right? Because of you're trying to load fast because with your finger, right? And the needle is very small, so the water can just a specific amount of water can escape per unit time. So there is a pressurization of the water inside the valve of the syringe, inside the open part. So what you end up having in this situation is what's called an undrained condition. Okay? So here's our system, the load is imposed, and what happens is the particles, yes, they want to move and attain this condition here, but because the water has a very hard time escaping, then the particles pressurize the water. Okay, and it takes very long for this condition to be attained, and therefore it takes very long for the water to escape, because those two processes are occurred together, right? The process of attaining this configuration with the process of water escaping. If the water doesn't escape, then the particles cannot achieve this configuration. So it takes time for the water to flow through the soil, through those very tiny pores, in the case of clay, for example, and for the system to attain this configuration. Okay, now, what causes the water to flow? Well, the additional pressure that is imposed by the loading. So when the loading is imposed, the water in the pores carries the load. Okay, and that's key. And it's kind of weird to say it, but when the loading is imposed in an undrained condition, in which this ratio is high, okay, then the water inside the pores is the system element that is carrying the load. The particles don't even know that that load is being placed. The water carries it, carries the whole layer. The water inside the pores carries the whole layer that you have placed here initially. Then the water says, you know what, I need to escape, I need to move because I'm pressurized. Okay, so because it's pressurized, it decides to escape, right, some of it, and therefore as it does that, it gives the load that is carrying to the grains, and eventually the grains are the ones that carry the load that you place. But eventually could mean years after you actually construct this fill, and of course that time, a year or 2 years or 3 months or 2 days, that is something that we're going to calculate or learn how to calculate later on. But for now, it's important to know the concepts, of course. If the system, if the condition is an undrained condition, which means that this ratio is high, then what happens is that the water carries the load, as we said. It carries the delta sigma that is imposed. The particles don't even know the load is there at that moment in time. And because the water carries the load, it gets pressurized. In fact, it's the same thing to say that it's the same thing to say water carries load than to say water is pressurized. Okay, the water is pressurized by the load. The load is equal to the amount of added pressure, and that added pressure is called UE, the excess pore pressure. Okay? Now, in the case of a poorly undrained condition, where the drainage rate is 0, if the drainage rate is 0, then the soil can never achieve this configuration. That is, if the water cannot escape, then the soil will always remain like this. And the water will always hold a UE. That can be imposed in the lab. Sometimes in the lab we do this to test the undrained strength of a soil, but that comes later. Okay? But in the field, there's always somewhere for the water to escape, for the excess water to escape, because remember that the soil remains saturated during the process. So the water eventually escapes so that the soil looks like this upon loading, right? Upon loading, the water gets pressurized, and then after some time the soil eventually looks like this because it takes some time for the water to escape, the excess water to escape. So this is kind of this here in the box is kind of a unique situation where there is no change in void ratio, there's no deformation of the soil, really very little. It's basically the compression of the water, that's it. There's no major volume change because the particles always remain in a configuration like this. That can be imposed in the lab, because in the lab we can close all the valves in the test setup and can prevent the water from escaping, but in the field the water always finds somewhere to go. So eventually we end up with a soil that looks like that. Let's say, if it started like this, it ends up looking like this. Okay, the important thing, or this is all very important of course, but the major thing here is that when UE is generated, then we have what is called an undrained condition, and when UE is not generated, or basically very little and quickly dissipates, quickly disappears in time, we have what's called a drain condition. Now, in current times, we have a coincidence of the following. When we have a coarse grained soil, sand or gravel, we have essentially, we can say that we have a high drainage rate because the hydraulic conductivity is high. Okay. Now we have to compare that to how fast we drop the water table, for example, or another example in our class is to place a fill above the site, right? We have to examine how fast we do those things, which are the construction operations, versus the drainage rate. In current times, we construct slower than the rate at which the water can escape the soil. So what we expect in the field is that if we have gravel or sand at the site, for example, if we dewater, which means reduction of the water table level, or add a fill, or both, we can expect drain conditions. That is if we have coarse grained soil, because of the typical rate at which we conduct engineering operations. If we have silt or clay, particularly clay because it has a very low K, then we can expect undrained conditions because we construct faster, drop this or with a pump or whatever, or construct faster than the rate at which the water can escape clay or silt. So you can expect in general that in the field, when you construct on sand or gravel, UE will be 0, and therefore you will have a drain condition. And if you construct on silt or clay, then you will have an undrained condition where UE will be non-zero, and will eventually be 0 when the soil achieves the final fabric it will achieve. Now, this is typical, but this doesn't mean that a sand or gravel can be loaded in an undrained manner. or that a clay or silt can't be loaded in a drained manner. In fact, if you have sand, for example, a sand mass that is saturated and an earthquake comes, then yes, you have a high drainage rate because of a high K, but the loading rate of an earthquake is very fast. So you still have this ratio being high, and you can get an undrained condition in sand, in which case you can get liquefaction of the sand, which means that the sand turns into quicksand. And anything above it basically sinks into the quicksand. That's a major problem that we have to be aware of in terms of seismic events, and to understand that process better and to learn about it and how to describe it and determine if a layer indeed will liquefy, etc., you can take the graduate course Soil Dynamics. Okay, but that's beyond, of course, the scope of this introduction class. Now, on the other hand, also you can have a clay or silt, and you can construct so slowly that you can maintain the UEs at zero by constructing slowly, meaning that the drainage rate for clay is very low, but you can construct even slower. Okay, that is very unusual, because if we construct slowly, we typically lose money. Okay, so you can imagine that we want to construct as fast as possible. Okay, this slide is very, very important because it will come up in all sorts of other, the concepts will come up in all sorts of other topics: strength, behavior in the field, settlement, etc., all that. Okay, so it's very important. This here, the UE, very important. To finish off this, let's go back to this slide and look at this right here. We already implicitly said this, okay? UE is generated when we load a soil and the condition is undrained, okay? And then eventually the water finds its way to escape the mass of soil, such that the soil still remains saturated, okay? But as the water escapes, the UE is transferred to sigma prime. So the load that is initially carried by the water, in time, is transferred to the particles, so that now the particles carry whatever load was imposed. Okay? So eventually UE becomes zero, and all of what UE was is added to the initial effective stress. Okay? So this is shown in the following slide. Actually, no, here we have one slide, and this is a parenthesis slide. Just go like this to it. Essentially, this is saying that because consolidation is a function of K, as we had seen there, right? The drainage rate is a function of K. So because consolidation, the process is a function of K, and K has units of centimeters per second, and this is time, then we know that consolidation is time dependent, and we already mentioned this, right? UE becomes zero, etc. Consolidation takes time to occur. The densification of the soil from this configuration to this configuration takes time, provided that, of course, the condition is undrained. If the condition is drained, this takes also time, but it takes seconds. Okay? If the condition is undrained, it may take years for this to happen, because it may take years for the water to be able to squeeze out of the voids.